Okay, we were discussing the programming model of 8085 microprocessor. So we've seen that there are 6 general purpose registers, which we call as B, C, D, E, H, L. So all of these are 8-bit registers. So they can be used by the programmer for writing any program. Okay. Apart from these 6 registers, we have one important register which is called as accumulator A. And the result of all the arithmetic and logic operations, it gets stored in accumulator A, and accumulator has to be one of the operands in that case. Okay. And then we have discussed flags. So you've seen that there are 5 flags in this processor. You have carry flag, then you have sign flag, 0, parity, and auxiliary carry. So these are basically 5 flip-flops. Okay, and they are set or reset according to the results of arithmetic and logic operations in the accumulator. Okay, so when you perform any arithmetic and logic operation, it is performed between accumulator and one more operand, and the result gets stored in A. And depending upon that result, these flags, they provide the status of the result in the accumulator. So if the sum or the number in the accumulator is 0, your 0 flag is set. If it is positive or negative, depending upon that, your sign flag is set or is set. Okay. Similarly, if a carry is generated, your carry flag is set. If you have even number of ones, the parity flag is set, and similarly auxiliary carry. Okay. So there are 2 more registers in that programming model. One was, so you have 6 general purpose registers, accumulator A, then you have flags B, C, D, E, H, and L. So all these are 8-bit registers except flag. Flags, we have 5 flags. Okay. Although we also indicate a flag register in which 5 bits are used to store these information, so 3 bits are unused. Okay. And apart from this, we have 2 16-point registers. One is PC, program counter, one is stack pointer. So this is 16-bit, this is also 16-bit. Okay. And then we have said, okay, we have a address bus here, and we have a data bus which is 8-bit. Address bus is here 16-bit. This is what was the programming model that we have discussed. Now say these 2 registers, program counter and the stack pointer, they are called as memory pointers. Okay, they have the same purpose, but they are used slightly in a different, you can say, way. What is program counter? Program counter, basically it holds the address of the next memory location. From which you are going to fetch the next byte. Okay. See, when we have discussed this microprocessor, how it works, so you interface some memory with it. Okay. You have a group of wires which we call as the address bus, the data bus, and then the control bus. Okay. So different memory locations, you write some instructions in the memory locations. Now when the processor starts executing these instructions, how it happens? You have to first identify the location of the memory location from which you are going to fetch the instruction. Okay, and how that is done? The processor has to place the address of that memory location on the address bus. Okay, first thing that has to be done. Okay, so first thing is that you have to first identify the memory location from which you are going to fetch this instruction. Okay, so this memory has a unique address which is a 16-bit address. So let us suppose if the address of this is 20,000H. Okay, and at this location we have some number, suppose 25H. Now this is operation code, opcode. Okay, because since you're fetching the first code, so first code is always a operation code, opcode. It is instruction, it cannot be data. Okay, after that it can be instruction, it can be data, depending upon whether it is a 1 byte or a 2 byte instruction or a 3 byte instruction, whatever it is. Okay, so the first thing the processor will do, it will place the address of this memory location on the address bus. It means your 2000H will be placed on the address bus. Okay, and how it is placed its address on the address bus? This data must be stored in some registers which can be put on this address bus. Okay, it will not come in the air. So which register is used to store that address? That is what is done by the program counter. Okay, so program counter, which is a 16-bit registers, since your address bus is 16-bit, so the size of this register is also 16 bits. Okay, so it basically stores or it holds the address of the memory location from which you are going to fetch the instruction. Okay, now see, it means when the processor will start executing the program, what will be the first step? The address of the location will be put on the program counter. Okay, or you can say whenever you restart or you start this system, the contents of program counter will be automatically loaded with the address of the memory location from where you are going to fetch the first byte. Okay, so if you have some program stored in a memory, okay, and suppose you have started writing the program at some location, maybe 20,000H, sorry, 2000H, 2001H, and so on. Okay, it means when you start executing the program, the processor should fetch the first byte from this memory location. Okay, now who holds the address of this location? That is stored in the program counter. Okay, so when the processor starts the execution of the program, so the first thing that happens in the processor is the address of the memory location is basically loaded in the program counter. Okay, and if you see in a microprocessors we have reset button. Okay, when you reset the microprocessor, the program counter is automatically loading with the starting address, that is 000H. Okay, but if you have some program which is stored at a different location, okay, not at the starting memory location, then the program counter must be loaded with the address of that location. So program counter holds the address of the location from where the execution has to be started. Now so your program counter is loaded with 2000H, okay, 16-bit number. The processor will move this data or place this data from the program counter on the address bus. Okay, now your address is located, and then it will send a control signal that we have discussed. It will send a read signal to the memory. Okay, and whatever is the data on this location 25, it will come to the database, and through this database there is of course internal database that we will see when we study the detailed architecture. So this data will be placed on the database and it will come inside the processor. It will be stored in the instruction register. Okay, and after instruction register it goes to instruction decoder where it is decoded, and the processor comes to know what is the purpose of this instruction, and accordingly that task is executed. Okay, so this is one complete instruction how it is executed. So fetch it, you decode it, you execute it. So you load the program counter first with the address of the starting memory location. So that contents of the program counter are then placed on the address bus. Your memory gets location gets identified. Processor sends the control signal read. The data is placed on the data bus. It comes inside the processor, given to the instruction decoder. The instruction is decoded and it is executed using the timing and the control circuit. Okay, so the timing and control circuit basically used to send control signals to activate specific functional modules or the logic circuits which perform that operation. Okay, now see, once you have loaded the program counter with the starting address of this memory, now since we have seen that the processor is a sequential, you can say, machine, it operates in a sequential manner. So it fetches the first instruction, decodes, executes, then it goes to the next location. It means your next instruction will be stored at 2001H. Okay, so what should happen? It means when the processor has fetched or it has located the first memory location, then it has to fetch it, decode it, execute it. So by the time when the processor is decoding and executing this instruction, this program counter should have been incremented by 1 so that it points to the next memory location now, that is 2001H, because the next byte is to be fetched from this memory location. Okay, so that may be an instruction, that may be data, whatever it is. Okay, this is what is done. Okay, so the program counter starts incrementing one by one automatically. So as the instruction is fetched, it goes inside the processor. So during the time when the processor is executing and decoding the first byte, the program counter gets incremented by 1 so that it points to the next memory location. Okay, so that is why we say that the PC, it holds the address of the next memory location from which you are going to fetch the next byte, because current location it has already identified. Okay, and the instruction has been fetched, it has to be decoded and it is going to be executed. So by the time the processor is decoding is executing the instruction, what the PC should do, since it has to take the data from the next location, so by that time it should have been incremented by 1. So it always holds the address of the next memory location from which you are going to fetch the next byte. Okay, so this will go like this. Okay, so the program counter initially will be loaded with the starting address, so that instruction at that address is fetched. So once it is fetched, the program counter is now free because that address is now identified. Okay, so it has to be incremented by 1. So the contents of PC will be incremented by 1 and it will be again now loaded on your address bus. So next memory location is identified. Okay, so the data on that is again placed on this data bus using the control signal that is given inside the processor. It is decoded and executed and so on. Okay, so it will go on like this till the processor stops the execution of program. So program counter is a very important register in microprocessor. So the size of this is basically compatible with the size of the address bus. Since address bus is of 16 bits, so program counter is also a 16-bit register because it holds the address, not the data. Okay, program counter simply holds the address of the memory location, nothing else. Okay, and the contents of the program counter, they are basically loaded on the address bus. Okay, because see, you have to locate the address, you must have some data on the address bus, and the data should come from somewhere. So from where it is coming from the address, your program counter. Okay, and as that instruction is being fetched, decoded and executed, so by the time the program counter gets incremented by 1. So this is internally done by the processor itself. Okay, once the program counter has identified this memory location, so by the time it fetches the instruction, decodes and executes it, it will increment program counter by 1 so that it points to the next memory location. from which you are going to fetch the next byte. So you will see all these things in more detail maybe when you discuss the architecture and the timing diagrams, in fact. Okay, because the timings of the signal, that is very important. Okay, so when you have to place the data on the data address bus, when you have to generate this read signal, and when the data will be come inside the processor. So these things are very important. So that all is decided by the clock signal. Okay, so the frequency that basically at which the processor operates, right? So the more is the frequency, the higher is the speed, of course. Okay, so you will see there are many terms like machine cycle, instruction cycle, and then there are T states and so on, right? So this is what is the significance of this register: program counter. Okay, so program counter, which is a 16-bit register, so it holds the address of the memory location, right? Similarly, we have another register which is called a stack pointer. A stack pointer has the same function similar to your program counter. It also holds the 16-bit address. This is also a 16-bit register. It also holds the 16-bit address of the memory location, but not for the memory where we have written your program. It holds the address of a memory which is called as stack. Okay, the stack is a, it is also a part of the same memory. So you have memory, in that memory you have programs, you have data, and stack is also in the same memory. It is not a different memory device. Okay, we have one memory, so that memory, in that same memory we have fixed some particular locations of this memory. They are fixed for stack. Okay, so that memory which is used for stack, that should not be used for writing the programs and the data by the programmer. Okay, means the main program should not overlap with the stack, although the stack is a part of the same memory. Okay, so you have certain locations that are fixed. But the difference between this memory stack and the other memories is that it is a structured memory basically. Okay, you store the data in the stack in a structured form, not in a random form. Okay, so in this part, which is a random memory, data can be stored in a random way, but every time you store the data or you retrieve the data from a memory, you must know the address of the memory location, otherwise you cannot. Okay, that is not the case with the stack. So in the stack we have only one register which is called as a stack pointer, and that is sufficient to locate the address of all the memory locations. Okay, because the data in the stack is put or stored in a organized fashion. It is not stored in random. It means if your one byte is stored here at some memory location, the next byte will be stored here only. The next byte will be stored here, here, and here, here. Okay, so it is just like you have one thing, you place some another thing over it, then place over it, place over it, place over it, and so on. This is stack. Okay, you can, if you're, you cannot write some data here and then from here you can directly go to here. This is not in the stack. Okay, so the data is stored in a organized way, and whatever data is written at the end, that comes first from the stack. Okay, so if you have something like this structure, if you, this is one brick, another brick, another brick. Okay, so you stack them together. So when you take out, you have to take first this, then this one, then this one, and so on. Okay, and this is what actually happens in the stack. Okay, so it is last in first out. Okay, the byte which you have stored at the end, it should come first from this stack, then you can retrieve this memory element, this one in a sequential way. Okay, so what we need in the stack is to simply remember what is the address of the top of the memory location, top of stack. Okay, so that address is basically carried by your stack pointer. Okay, so if you know, okay, that the stack, the data in the stack or the top of stack is here, so if you want to retrieve the information from the stack, so you can just go one memory location below this and you can start retrieving the data. Okay, or if you want to write some data, so you can write the data about this stack, and automatically your stack pointer will either be incremented or it will be decremented. Okay, so but there is one difference in the stack pointer and this program counter. It is incremented or decremented by 2. Okay, because when we will discuss in this is a separate chapter on stacks, of course, when we discuss in the stacks, so you can store or you can retrieve 2 bits at a time. Okay, so either you can retrieve 2 bits at a time or you can store 2 bits at a time. Okay, so accordingly the stack pointer register, which holds the address of the stack, it gets incremented by 2 or it gets decremented by 2 accordingly. Okay, so it means if you want to access the stack or if you want to define the location of the stack in the memory, so the first thing is that you must load the stack pointer with the 16-bit number, which is nothing but the address of the top of the stack. Okay, so that has to be done. And generally we use stacks for those applications where you need a program in the main program. If you want certain function or certain program to be called again and again, like suppose just I have taken example of delay. Okay, so you have a traffic light system. If you have a traffic light system, so you have 3 lights, you have red light, blue and green. Okay, so you have to turn this light for some time, then create a delay of 10 seconds, suppose, then turn on another light, then create a delay, turn another light, and so on. So which program is basically frequently being used now in this? That is a delay subroutine, delay program. Okay, it means either one way is that when you write the main program, so you write the program for the delay in the main program itself, and every time you have to write the programs, so you have, it will take so many, you can say, memory locations now to store this program. Okay, so otherwise what we can do, you can write a separate program for that which we call as subroutine, and this now subroutine will be basically stored in stack. Okay, the starting of the stack has to be specified by loading a 16-bit address in the stack pointer. Okay, so every time you need to you need a program for creating a delay, so you just write instruction in this main program, a jump instruction, or in fact a call instruction here. So this call instruction is a 3-byte instruction which will be used to call a subroutine. So the program is transferred from the main program to the stack. Okay, so there is no program for delay here. So this program is executed, it will create a delay, and after this subroutine is finished, it should again come back to the main program from where it has jumped. So for that we have instruction return. So every instruction where you, whenever you write instruction for call, it has to be written ended with a return instruction. So call and return, they are used basically. So if you have used call in any program, so it means you are transferring the control or you are jumping the execution of program from one memory location to another memory location. And at that memory location, we have basically a subroutine, which is a specific, you can say, task or purpose, just like for creating a delay. And then after executing that program, it should come to the main program. So that is done by this RET instruction. Okay, So since this program is now used again and again, you have to turn on the green light, then get a delay, turn on the blue light, turn on the red light, and so on. So you cannot write the program again and again in the same memory location. Okay. So in fact, we have separate memory locations identified, which is stack, and you have already specified the address of the stack from where it is going to be started. So this is up to you. You can locate the stack at any point. It's not fixed. Okay. It's up to the programmer. So you keep certain bytes fixed for stack. Okay. So that you have to specify by writing some address in the stack pointer. Okay. So this is what is stack pointer. Okay. Of course, we will come to this stacks and subroutines in a bit more detail. We have instructions for this, which we call as push and pop. Okay. So these are the two main instructions which are used in the stacks. So using the push instruction, you basically put a 16-bit data on the stack. Okay. 8-bit at one memory location, 8-bit at another memory location. So using pop, you retrieve this data. Okay. So when you use the push and the pop, the stack pointer automatically gets incremented or decremented by 2. Okay. Because 2 bytes they are written at a time, or 2 bytes they are retrieved at a time. So the program counter it gets incremented by 1 only. Okay. Because you are fetching the data in a byte by byte format. Okay. So next we will see some classification of these instructions. Okay. And then how we classify into data transfer and your arithmetic logical instructions and so on.